pop your solar probe is a mission to explore the sun. How can it do that?
Can do that.
Why won't the spacecraft melt? Excellent question.
Why won't the spacecraft melt? Excellent question. That is a classic. How can it do it? Why won't the spacecraft melt? Right, it's got a gallon of water in a radiator. That's why. Right, the first rule was to get Earth and the Moon to scale, okay? So we divided Earth's diameter by the Moon's diameter and we get 3.6. This is a 30 centimetre diameter globe. So we divided it by the 3.6 of the result of the Moon and Earth, and we get 8.3 centimetres. That is 3.6. So 1, 2, 3, about 6. Within a couple of millimetres, right? I've had this for a long time. Number one, out of the way. Right. So a couple of things, and then we're going to go out to the field. Right. So let's focusing on these two boards now. Right. Usually when I do this, it's always the sun first. So we build the sun and then everything to scale after. Today it's been about Earth because of that YouTube thing where Al and Mr. Tyson were talking about the eclipse, and it was a little bit out. Right. The average distance between Moon and Earth is 384,000 kilometers. If we divide that by Earth's diameter, we get 30. So there are 30 planet Earths in between the Moon and us. 1, 2, 3, 4, right? 30 of them. Its diameter is 30, so we've got 30 of them. 30 times 30, 900. So 900 centimeters is 9 meters. So the distance that we're working with out there is 9 meters. That is the distance to scale, right? No, we had, what do we have? 1.27 and a 2.5 millimeters. And it was on a card. I wrote on a piece of paper, and it was 7.5 centimeters, right? That was to scale. So now we're at 9 meters. So what I had on a piece of paper like that is now 9 meters. But the sun was, I doubled it, didn't I? So it was 278. But we've more than doubled here, right? So 9 meters is what we've got out there. What we have now is the sun's dimensions and the distance between that Earth and this Moon and the sun, right? So what we do, we've got, don't rain again. We've got 150 million kilometers, right? The distance between the sun and us. We divide that by the sun's diameter and we get 107.9, right? If we divide the sun's diameter by Earth's diameter, we get 109. So there are 9 planet Earth's diameters in the sun's one diameter. If we divide the distance, the 150 million kilometers between us and the sun, by Earth's diameter, we get 11,772. So there are 11,772 of these in between us and the sun. 1, 2, 3, 11,000 of them. The sun, there's only what, 109, 107.9, 108, right? 11,772, and the sun's only 108, right? That's the scale we're talking here. Right, we've got 109 Earths, right, multiplied by 30, right? So we've got that 30 centimetre, we multiply that by the 109 of them, and we get 32.7, right? The sun, the diameter of the sun is 32 meters, right? This is to scale. So if this were really Earth, the sun would be 32 meters. That's like a what? 3 meters in a big apartment. That's a high roof, isn't it? 3 meters. 10 floors. Boom, boom, boom. 32 meters. That's the diameter of the sun. That is what we're going to be thinking of when we go outside. So we're basically looking at a 10-story building or 11-story building, right? And the 32.7, we need to multiply that now by the amount of suns. That gives us the distance, if you know what I mean. It gives us the 150 million, right? So that's the sun's diameter multiplied by the 107.9. That's 3.5 kilometers. This is all to scale. You can double check it. So we've got this. If this were for real, planet Earth, this size, the sun would be 3.5 k's away, and it would be the size of a 10-story building, right? 3.5 k's away to scale. Now, 3.5 k's, right, isn't really that far. If it was a dark night and you're on a beach and somebody put a torch on, a flashlight, you'd see it instantly, right? Don't forget that. No, you can't use a bulb. Well, now we're using a 11-story building is the sun, and it's only 3.5 k's away. That's the scale. Still think it takes 8 minutes and 20 seconds for that light to get from that 11-story building that's only from here to Kalki away. If that, it's to scale, right? It's going to be the same story all the way up till you get to 1,390,000. It's illogical to think that light travels that slowly. It's ridiculous. And it's there again. And I only just saw that. Right. Boom. So 3,528 meters away. That's how far the sun is from where we're going outside now. And this is a final check. So the sun's diameter is 32.7. The Earth's diameter is 30 centimeters. So if we do the sun by the Earth, you divide diameters, we get 109, right? Sun, Earth, 32. Alexa, what's 32.7 meters?
32 is a number.
Alexa.
32 is preceded by 31 and succeeded by 33.
Doing this lately. Alexa, what's 32.7 meters divided by 30 centimeters?
32.7 meters divided by 30 centimeters is 109.
There we go. Right? It's bang on to scale. That's how you double check these things. The distance Earth Sun is 3.5 kilometers. That's 150 million. So we want to divide it by the sun's diameter. Alexa, what's 3.5 kilometers divided by 32.7 meters?
3.5 kilometers divided by 32.7 meters is approximately 107.0336.
Right, so I round the numbers up, so we lose a little bit, but they're bang on, all right? There is no doubt. I've worked it out. This is to scale. Tell me I don't know my numbers. Right, let's go and have a look now. Now you've got the distances in your head and the sizes. Let's go and see what the dough is. Torch. And where's that? Oop. Once more.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that?
How can it do that?
Why won't the spacecraft melt?
Why would no?
Excellent question.
Excellent question. Excellent question. Excellent question. Why won't it just melt? Let's make sure they sweep the runway properly before they leave. All right. Ooh, what was that? What's that? Oh, nothing to write about. Right, so we're going to put the Earth here. So here's what we've done with him. Obviously measured 9 meters. Let's go over to La Luna's position. 9 meters. This is 384,000 kilometers. Right, where is it? Should be around about here. Right. Okay. Look at this tomorrow during the day as well. That's the moon. That's Earth. Right? Now look at this. Don't forget what we're looking at here. So you're going to be, those of you in the US, right? Let's zoom in a bit. So you guys are going to be where the light is shining on you right now. Right? So you're going to be, I'm not going to run over there and turn the US this side. You're just going to have to trust that that's going to be you guys, right? And we are right next to the moon. So this is what's going to happen. First of all, don't forget, what you're dealing with here is 3.5 Ks that way, right? And it's 10, 11-story building, and it's the sun, right? 3.5 Ks away. If you jumped on the roof of this house and it was a flat road, you'd see the sun from here. You'd see that building from here, wouldn't you? 3.5 Ks, it's to scale, right? Tell me that it would take 8 minutes and 20 seconds. It doesn't matter how you look at this thing, because you can next go up to a planet Earth that's, I don't know, 1 meter, right? And then the sun will be like 11 Ks away, but it will be the size of getting towards skyscraper. You keep going along like that, and you're always going to have the same scale. When does it suddenly go to 8 minutes and 20 seconds for the light to travel that distance? It's an absurdity. The more you think about it objectively, it's the only way to look at it. It's ridiculous. Right. So, the sun is 3.5 k's back inside the building, but can you see, sorry, my bad, the shadow? And this is a flashlight, right? See that shadow behind us, behind Earth? This torch, right, because the sun, where it's at 3.5 k's, that's how far back we'd have to go now, right, for the moon to look like the same, well, to be the same size as the sun behind it. Because any closer, that looked like a gigantic mouse. And now it's turned into a cat. Those clouds. That was bizarre. Looks like two front paws. Freaking, that's clouds. This foam makes everything look freaky. So you see what I'm saying? If we get up close, so further away you go, obviously the smaller, so I'm going to go right to the back fence here. It looks like, actually I can do that again so you get a closer. It looks like the moon is gigantic, but that's only because, it's really small, but that's only because I'm not 3.5 k's away and I'm not an 11-story building. I'm going to turn the light off in the shed. Okay, here we go. So, because we're close to it, the further away I go. And another thing, right? Another thing, thinking about that. 8 minutes and 20 seconds. It's not even worth thinking about. I was just going to say that the sun, it's not even worth talking about. How is the sun going to be 8 minutes and 20 seconds further ahead just because everything gets bigger? We are to scale right here, okay? And to scale is to scale. Even this has just disproved that 8 minutes and 20, unless you've got no common sense, all right? To me, it's a slam dunk. The distance gets bigger, but so does the sun, and it stays in proportion all of the way. If you want a bigger sun, or you want a bigger distance, you get a bigger sun. There's no way out of it. It's thing is 1,390,000 kilometers, crying out loud. Does not take 8 minutes and 20 seconds. It's too big. They are downplaying the power of the sun. That's what they're doing. Trying to say that it takes 8 minutes to get here, that they can send a solar probe because it's not too hot. Other than hot and not. Rubbish. Just bring the planet in case it rained, but doesn't really matter, does it? Alright. So that's it. Right? You can say all the words you want about an eclipse, but you've got to see it. You've got to see it to scale. Otherwise, what are people thinking, that the moon's this big? And you've got to see it. You've got to physically see this stuff. It's the only way of doing it. Otherwise, you don't. It's all very well good to draw it on paper, but no, you don't put anything into perspective ever if you just keep doing that. And you lose sense of the real measurements and dimensions and do you know what I mean? So, boom, that's your eclipse. Record it. I heard something today about, they're saying something about not looking at it or trying to make it sound dangerous. I don't know, I didn't get the full story. I've seen about 4, 5, maybe even half a dozen full eclipses of the sun in my life, because I've been in the right place at the right time. I've seen loads of partial eclipses, and I've looked at every single one. I look at the sun a dozen times every single day, right? I just look at it for a couple of seconds, and I get that little dot. They're trying to dumb everybody down and make everybody scared of everything. It's rubbish. Nothing wrong with looking at the sun every now and again. It's our life source. Alright. Well, that's my chess. That was a good one. I enjoyed it anyway. Hasta la vista. Oh, once more. Come on, right. Chop chop. Alexa, I didn't say hello to you tonight. How are you?
Thanks for letting me know, so I can learn from my mistakes.
Yes, Alexa. Please. Do. Gosh, she's a shocker. Right, where is it? There we go.
NASA's Parker Solar Probe is a mission to explore the sun. How can it do that? Why won't the spacecraft melt? Excellent question.
Excellent question. Love it.
You can't face off with the sun without packing the right gear.
That's it.
This is why Solar Probe is equipped with a white shield that reflects heat off the front to keep...
Alexa, does the colour white reflect heat or light?
According to an Alexa Answers contributor, white does not attract heat, it reflects photons.
Yeah, alright. Good night. Alright, hasta la vista. I'll be back with some more solar pro. Oh no, hang on. Yeah. I'll throw some solar probes in tomorrow. No! Tomorrow, do a little bit more on the eclipse and working out the speed of light. That's what we'll do tomorrow. Later, peeps.